Almost all 33.9 kilometers of the seawall were in place, but the hardest part was still open. Only 2.7 kilometers of open water remained across two final gaps, and as those openings became smaller, the tides were forced through less and less space. During the final closure, currents could reach up to 7 meters per second. Now engineers had to fill those gaps with rock, control erosion around the unfinished structure, and keep advancing while the water itself became harder to control. So how did South Korea close the sea? The answer begins with the scale of what engineers were trying to build. The Saemangeum seawall stretches 33.9 kilometers along South Korea's west coast. It is recognized as the world's longest seawall, but the word wall creates the wrong picture. This is not a thin vertical slab of concrete standing in the ocean. It is a gigantic earth and rock embankment. At some sections, it rises more than 50 meters, and beneath the surface, its base can spread more than half a kilometer across. At its widest, the foundation reaches roughly 535 meters. That makes the structure less like a conventional wall and more like an artificial ridge built across the sea. Creating it required approximately 123 million tons of earth and rock, and all of that material had to survive a coastline controlled by tides, waves, and moving sediment. Construction began in November 1991. At the time, Saemangeum looked completely different. The Mangyong and Dongjin river systems opened into a broad tidal estuary connected directly to the Yellow Sea. Mudflats, channels, and shallow coastal water expanded across the area. With every tide, large volumes of water moved in and out. The original development vision focused heavily on reclaiming land for agriculture. That vision would change considerably over the following decades. But none of those future plans could begin until engineers solved the first physical problem. How do you build almost 34 kilometers of embankment across a tidal seabed? Before construction could advance, engineers had to understand the coast. They needed to map water depths, study tidal movement, examine wave conditions, and understand how the seabed changed along the proposed route. A structure this long does not sit on one identical foundation. Depth, sediment, and exposure vary from section to section. Detailed foundation treatment records for every part of Saemangeum are not fully available in public sources, so close technical reconstructions of those processes must be treated as representative coastal engineering methods. But the overall construction logic is much clearer. The seawall could be advanced progressively. Material was placed outward from existing land, islands, and completed sections of embankment. Every stable section created a new construction platform. From there, trucks and heavy equipment could move farther into the sea. Then the process repeated. Place material, shape the embankment, protect the exposed face, advance again. Kilometer after kilometer, the working edge moved farther from the original coastline, and feeding that construction front required an extraordinary amount of material. Approximately 123 million tons of earth and rock went into the seawall. That material had to be excavated, transported, and placed at a scale large enough to resist long-term marine forces. But engineers could not simply dump everything into the water at random. A sea dike works because different parts of the structure perform different jobs. Its enormous body provides mass. Its broad geometry spreads loads over a large area. The outer face must withstand direct wave attack. Large armor stone helps absorb and resist that energy. Graded material behind the armor helps protect the finer material inside the embankment from being washed out. And the upper surface eventually becomes a stable crest for roads, maintenance access, and permanent infrastructure. At full scale, even heavy construction equipment becomes small. A dump truck moving along the crest can look almost insignificant compared with an embankment whose base is hundreds of meters wide. But size alone does not make a seawall safe. While the structure was still incomplete, every exposed section remained vulnerable to the Yellow Sea. Waves could attack unfinished slopes. Currents could erode newly placed material. And water continued moving through the openings left between completed sections. so protection had to advance with construction. On the seaward side, large armor rock helped break up incoming wave energy. The broad, sloping face reduced the concentration of force. Protected inner material helped prevent the gradual loss of the embankment body. Official specifications used a 1,000-year design wave criterion, with different design wave heights for different sections of the seawall. That does not mean a single 1,000-year wave was expected to strike the entire structure. It means the design had to account for rare and severe wave conditions appropriate to different sections of the barrier. But building a structure strong enough to resist the sea created another problem. What happens to all the water behind it? Rivers do not stop flowing because a seawall exists. Rainfall does not stop. Floodwater still has to escape, and some exchange with the Yellow Sea still needs to be controlled. So Saemangeum required enormous hydraulic gates. 2 major sluice systems were constructed at Garioch and Cinci. Together, they contain 18 major gate bays. Each bay is roughly 30 meters wide, and the 2 systems have a combined official flood discharge capacity of about 15,862 cubic meters per second. Instead of allowing the entire estuary to remain freely open to the tide, these structures created controlled points where water could move between the enclosed Saemangeum system and the sea. That distinction is critical. The project was not designed simply to trap water permanently behind a wall. It replaced a broad, uncontrolled tidal connection with an engineered hydraulic system. And once those gates and long sections of seawall were in place, construction entered its most difficult phase. Most of the barrier had already been built. Several openings still allowed tidal water to pass through the alignment. A northern opening was closed in 2003. Then only 2 major gaps remained. Together, they totaled about 2.7 kilometers. One was approximately 1.6 kilometers wide. The other was approximately 1.1 kilometers. For most construction projects, reaching this point would mean the hardest work was nearly over. At Saemangeum, the opposite could happen. When a tidal opening is wide, water can move through a large area. But every time engineers reduce that opening, the remaining tidal exchange has less space available. The flow becomes increasingly concentrated. Local current velocities can rise. Scour around newly placed material becomes more serious, and rock placed into the channel has to resist stronger hydraulic forces. The seawall was getting closer to completion. The remaining water was becoming more difficult to control. During the final closure operation, current speeds could reach up to about 7 meters per second, roughly 25 kilometers per hour. That number means very little if we imagine a car traveling on a road. Underwater, it means something completely different. Water moving at that speed exerts force across every exposed surface. Smaller material can be displaced. The seabed can scour around newly placed rock, and every change in the shape of the gap changes the way the next tide moves through it. This is why engineers could not simply drive to the edge and dump enough rock into the channel in one final push. The geometry of the opening had to be changed progressively. Published engineering studies describe a combined vertical and horizontal closure strategy. The vertical part began underwater. Before the remaining openings could be closed completely from the sides, engineers progressively raised the submerged sill beneath the flowing water. Rock and other closure material accumulated on the seabed. Placement after placement increased the elevation of the underwater structure. The visible opening might still have looked enormous from above, but beneath the surface, the effective channel was becoming shallower. That was important, because final closure was not only a problem of width, it was also a problem of depth. At the deepest portions of the final closure zone, reported water depths reached roughly 54 meters. So before the final gaps could disappear at the surface, engineers first had to build an enormous part of the barrier where nobody standing on shore could see it. The seawall was rising from the seabed upward. At the same time, construction advanced horizontally from the sides. Truck after truck carried rock toward the closure fronts. Material was placed into the flowing water. The underwater sill rose, the two gaps narrowed. But as they narrowed, the remaining flow became increasingly concentrated. That meant the final stages required material that could remain stable under severe current conditions. Engineers used rock together with bag-type gabions. Instead of relying only on individual loose stones, a bag-type gabion contains stone as a heavier, more stable unit. That makes the placed material more difficult for strong currents to move. The concept was simple. The execution was not. Every load placed into the gap changed the opening. Every change in the opening changed the water. And every new tidal cycle tested the work that had just been completed. This was the central paradox of Samangium. Every successful placement brought the two sides closer together, but it also concentrated the remaining water into an even smaller passage. The project had already consumed years of work and tens of millions of tons of material. Yet the final connection depended on controlling a comparatively small part of the entire 33.9-kilometer alignment. The last kilometers mattered more than all the completed distance behind them. Gradually, the underwater sill became higher. The closure fronts advanced farther. The gaps became narrower. Rock and gabions resisted the flow, and the amount of uncontrolled water able to pass through the remaining openings continued to fall. Then, on April 21, 2006, the two final gaps were closed. The last uncontrolled openings through the seawall alignment were gone. For the first time, a continuous 33.9-kilometer barrier stretched across Samangium. Nearly 15 years after groundbreaking, engineers had completed the defining hydraulic challenge of the project. But closing the sea was not the same as finishing the seawall. There were still years of work ahead. The completed alignment had to be strengthened and finished. Crest roads and permanent surfaces had to be completed. Protection works, access systems and associated infrastructure continued to develop. And on April 27, 2010, the Samangium seawall was officially completed. From groundbreaking to official completion, almost 19 years had passed. Those 19 years were not one uninterrupted construction campaign. The project went through reviews, suspension periods, legal challenges, and intense public debate. And the engineering achievement cannot be separated completely from the transformation it produced. The seawall itself cost approximately 2.949 trillion Korean won. The wider Samangium project is much larger. Current development plans cover about 409 square kilometers. But that number does not mean 409 square kilometers of new dry land were created. The wider area includes approximately 291 square kilometers of planned or developed land and around 118 square kilometers of lake and water area. The original agricultural reclamation concept also changed over time. Later plans expanded into industrial development, infrastructure, tourism, energy, and other uses. What the seawall created was the physical boundary that made those larger plans possible. It turned an open tidal coast into a controlled development system. And that transformation came with a major environmental cost. Closing the seawall changed tidal circulation. Large areas of mudflat and estuarine habitat were transformed. Fisheries and coastal ecosystems were affected. And later ecological studies documented major changes in migratory shorebirds that had used the Samangium tidal flats. Those impacts became central to years of legal and public controversy around the project. So Samangium is not simply a story about humans defeating the sea. It is a story about what happens when engineering becomes powerful enough to redesign an entire coastline. The physical achievement is extraordinary. A 33.9-kilometer barrier, a base that can spread more than half a kilometer across, approximately 123 million tons of earth and rock. 18 giant sluice bays controlling water between the enclosed system and the Yellow Sea. And two final openings closed, while tidal currents could reach up to 7 meters per second. For nearly 2 decades, engineers pushed an artificial ridge farther and farther across the coast. But the hardest challenge was not building the first kilometer, it was closing the last one. Because in marine construction, the closer a barrier comes to stopping the sea, the more difficult the remaining water can become to control. This is where coastal engineering meets the tide, and where 123 million tons of earth and rock became the world's longest seawall.